Hello, my name is Klemen.
My name's David.
And my name is Newman.
And this is our overview of absolutely everything in AP Physics C, Newtonian mechanics.
Newtonian mechanics is the study of the motion of systems under the influence of external forces. So external forces cause motion of systems. Now what causes these external forces? The answer is interactions between systems. These interactions cause external forces, which then lead to change in motion of systems.
Let's take a look at the interactions that occur in Newtonian physics. The contact interaction is the first up, and it is responsible for the normal force, the friction force, and the force of drag. Second up, we have the elastic restoring interaction, and this is responsible for the spring force. Up next, we have the tension interaction, and this one causes the tension force. Finally, we have the gravitational interaction, and this one is responsible for, well, gravity, or gravitational force to be proper. Let's take a more in-depth look at each one of these specifically. Contact interactions occur whenever two bodies or objects are in contact with each other. A great example of this would be a car crash. The two objects collide and exert force on each other. Now, the first of these forces is the normal force. The normal force occurs whenever two objects are in physical contact with each other and exert forces upon each other. They will exert a force that is equal in magnitude but opposite in direction. And these applies to both humans and Jedi. Secondly, we have friction. Now imagine you're cruising down in your car down the highway and you're going pretty fast and you see your exit and the light is green, so you kind of go a little bit faster. But then all of a sudden the light turns red and you have to brake. You squeeze your brake calipers and the road exerts friction on your wheels, which in turn slow down your car. Finally, there is drag. And drag is friction of objects moving through fluids. A great example of this would be an airplane moving through the air. Now, an airplane's engines will push back onto the air, which propels it forward, and the upcoming air will cause drag, slowing it down. Now, contrary to popular belief, this is not what causes lift.
Alright, so next we have the elastic restoring interaction. The elastic restoring interaction leads to not tension, the spring force. And most commonly, people think about a spring. Here we have a little demonstration of this spring force. We have a race between a tissue box and a whiteboard eraser. So we're compressing the spring to provide the spring force in order to push either the tissue box or the eraser. Here we're screwing up a few times, but obviously because the eraser has less mass, it wins. Brilliant. Alright, so next we have the tension interaction. The tension interaction leads to a tension force. Here we have a wrecking ball. Gravity pulls this wrecking ball down, while there's tension force in the rope that keeps this wrecking ball stable. You can imagine who that person is on the wrecking ball. So the tension force exists in tight ropes and strings. Most commonly this is demonstrated when you have tug-of-wars. Both hands provide force opposite of each other, but there's tension force in the rope that is parallel yet opposite to the force of the hands. And when the tension force becomes too great, the rope breaks.
Our final interaction is the gravitational interaction, and this causes gravity. Gravity is the attraction between any two objects that have mass. Those two objects are attracted to each other with an equal but opposite force. However, the more massive objects move less towards the less massive object. Now, another object that follows this law is the moon, and the moon should by all laws fall into the Earth. However, the reason why it does not is because it also has a velocity perpendicular to the gravitational force, and therefore it goes around the Earth instead of into the Earth. This, however, does not apply to incoming meteors, and so the dinosaurs were not as lucky as we were.
Okay, so there are four types of interactions that we covered in Newtonian mechanics. These 4 types of interactions lead to 6 forces, which leads to change in motion.
The change in motion depends on the line of action of the net force and the composition of the system.
There are 3 types of change in motion. The first is translations. The second is oscillations. Oscillations. Yeah, it's a difficult word. Lastly, there are rotations. So rotations. Rotations are when the line of the net force does not pass through the center of mass. David here applies net force not through the center of mass, so causes our friend George to spin.
So translations are when the line of the net force passes through the center of mass. Here I push this eraser through the center of mass and it translates across the whiteboard. However, if I push on the side, it rotates.
Lastly, we have oscillations. Oscillations is simply repeating motion. It could be repeating rotations or repeating translations. This pendulum is a great demonstration of oscillation.
Now inside this box we'll present our system. The first example will be a single body system, and this applies to the interaction of translation. Now, state variable for this is velocity. And the model we use is the net force model. As you can see, this is essentially us pushing an object within a system that is influenced by external forces. The second one is a multi-bodied system. Now, a multi-body system, its key difference from a single body system is that it includes multiple bodies or objects inside of it, and they translate energy between one another. The state variables are linear momentum and total mechanical energy, and the agents of change are impulse and work. We also have models to represent this. For impulse, we have the impulse momentum model, and for work, we have the work mechanical energy model. And as you can see, this is essentially 2 objects translating energy between each other.
Next we have single body systems for rotation. In rotation, the state variable for a single body system is angular velocity. The agent of change for angular velocity is torque. And we use the net torque model to describe this. So there's also multi-body systems for rotation. In a multi-body system, there's simply 2 or more objects exchanging energy and momentum through rotation. The state variables are angular impulse and angular momentum. The agent of change is impulse, which changes momentum, and work, which changes energy. So we use the angular impulse / angular momentum model and the work mechanical energy model.
Here's a system that the change in motion is oscillation. There's only single body system for oscillations, no multi-body system. And the state variable is linear velocity or angular velocity. And the model that describes the system is elastic restoring model. And in this case, what keeps the pendulum moving is the restoring torque.
Alright guys, thanks for watching. Signing off, Newman.
David?
And Klemen.